In this video, I'm going to discuss merge sort. Now, I've written a program here in the C programming language, and it's based upon the pseudocode in the book Introduction to Algorithms by Corman, which is a fairly popular algorithms book. If you look at other implementations, at least the ones I've seen in the most basic forms are basically this right here. You can do other things to try to improve memory usage or whatever, but most of the introductory versions you see were somewhat similar to this. So down here in main, you can see that I've created an array of ints, and there's 8 integers here, and they happen to be in reverse order, 80, 70, 60, all the way down to 10. And then I'm going to call merge sort the first time. And so I will give it the array name, the index for the beginning of the array, which is 0 in C, and the index of the last element of the array, which will be 7 in this case. And so we enter merge sort for the first time. So here I will refer to the array as capital A, and first and last will be 0 and 7. So now I ask the question, is 0 less than 7? And since the answer is yes, I'm going to calculate this midpoint. Now technically in the theory, it says what you do for the midpoint is you'll have first plus last divided by 2, and then you use what's called a floor function. So what I'm saying here is floor, and use that function, and when you do, that will round down to the nearest integer. Now in C, when you perform integer division, and since first and last are both integers, I have an integer result here divided by an integer, I get an integer as an answer. In C, integer division is performed by truncating the result. So here for the first time, what we can see is since first and last are 0 and 7 respectively, I have 0 plus 7 is 7 divided by 2 is 3.5, but since we truncate, we drop off the 0.5. And since the result here is a positive number, truncating will be the equivalent of a floor function for what we were doing. If I had a negative number, truncation and floor functions aren't actually the same, so I wouldn't be able to use this to get the result in that case. But indices will always be non-negative, so this will work. So we will get 3 in this case, and then what we do is we call merge sort again, giving it the same array name, so we're still processing the same original array, except now we're looking at the portions from 0 to 3. So we come into another instance of merge sort, in which first and last are 0 and 3. 0 is less than 3. We calculate the midpoint of that, which would be 1. And we call merge sort again for 0 to 1. And we keep repeating this until this fails, and then we pick up where we left off, which is now called merge sort using the other portion of the subarray we're looking at. And then eventually that fails, and then we call the merge function. So let's look over here and see what's happening. So this is what all these print functions are doing. They're printing the array and the indices that we're dealing with. So once again, this is the original array, and first and last will be 0 and 7. And then we call merge sort again. We're looking at indices 0 through 3. We call merge sort again. We're looking at the left half of that, which is 0 to 1. We call merge sort again, and we get 0 to 0. So when we come in and first and last are both zeros, this fails, and that's where we will then return to the merge sort that called this and pick up where we left off, which is to follow the right side. So when we do that, the right half of 0 to 1 will just be 1. So that means we come into an instance of merge sort in which first and last are both 1. We reach the end of the function and return to where we left off. And now we're ready to process 0 to 1, which means calling the merge function. So let's look at that. So here in merge, we create some variables. N1 will be the number of elements of the left half. N2 will be the number of elements of the right half for the portion of A that we're currently dealing with, which is just this right here. And then we're going to allocate some memory to store each half of that sub-array of A. But notice here that we're actually allocating memory to store one additional number, which I will explain in a moment. So now we're going to copy the left half of the portion of A that we're looking at to L. We copy the right half of A that we're looking at to R. And then we're going to put, in my case, 1 billion as the last element of each. So what these are what are called sentinel values. Eventually, we want to move through each of these copies of A, comparing the elements so we can recombine them into A such that they're sorted. But we need to make sure we don't go too far. So we could have the logic that would say if L is less than or equal to R and the index of L that we're working with is not greater than N1, or the index of R is not greater than N2, or greater than or equal technically in both parts, we'll then keep doing something. But what Corman does is they put these sentinel values in there, and these are values that we would never encounter naturally. In their pseudocode, they just say infinity. So that's why I've chosen these really large values here. And what will happen then is that when we're comparing L to R, eventually some element of one of the two arrays will be compared to infinity. And when that happens, the non-infinite value will obviously be the smaller of the two. So we don't need to look at how far into L and how far into R that we went. We eventually encounter infinity in one of the two arrays, and we know that it can't be the winner of the two. Okay? So after merge sort, after calling merge, we'd be at the end of that instance of merge sort, so we return where we left off and keep processing. So in this case, what has happened is when we combined the array that contained 80 and the array that contained 70, when we recombine those, we copy those in sorted order back into A as 70 and 80. So this is actually what array A looks like right now. So now we return to where we left off. At one point, we were looking at indices 0 and 1 of A. Now we need to look at indices 2 and 3. So we follow the left half of that, which is just 2 and 2. Follow the right half of that, which is just 3 and 3. And now we need to merge those, and we do. 60 and 50 becomes 50 and 60. And so this is what array A looks like now, this entire row. And then we need to combine those, and we do. We get 50 through 80. And we continue on down, then we process the right half, the left half of that, the right half of that, or whatever. Eventually it's sorted. So let's look in more detail about what is happening here in terms of what we see. So we don't technically create a binary tree, but it's helpful to understand what we're doing if we think of it as a binary tree. So originally, we have this, so 80, 70, 60, 50, ... I'm going to write all that out. Remember, our indices are 0, 1, 2, 3, 4, down to 7. And we look at just this portion that contains 80 through 70, or 80 through 50, excuse me. And so these are indices 0 to 3. And then we look at the left half of this. Which have these indices. Then we look at the left half of this, which is just 80. But now, in the merge sort function, this is a place where we have indices 0 to 0. So we go back to where we left off, and now we go to the right. And this has indices 1 and 1. This is at the bottom. So now we go back to where we left off, and we're ready to merge this with this. So if you know how to process a binary tree, what we're doing is performing a post-order traversal. So what you do in a post-order traversal is you go left, you go right, and then you do something in the current node. So here, we went left, went left, went left, bottomed out, came up, went right, bottomed out, came back up, and now we're ready to do something. So according to our merge function, what happens is we copy L will be equal to 80 and infinity, R will be equal to 70 and infinity. And then in terms of our original A, I'm going to write down here, we have 80, 70, 60, 50, 40, ... When we compare these, we say, well, 70 is smaller than 80, so copy 70 right here. So at this point in time, if we were to stop here, our array A says 70, 70, 60, 50, and so on. Now we compare 80 to infinity. 80 is smaller than infinity, so we use it, and we copy it there. And because we've used all the elements we need to use, this is what our array looks like: 70, 80, 60, 50, 40. So now we were here, we need to back up to here, and we need to go right again. So we have 60 and 50. We go left. This is 60. We bottom out. We come back up. We go right. We bottom out. We come back up. We're ready to merge. That's our do something. So our do something, in this case, is calling merge. So what happens? Well, now we'll say L is equal to 60 and infinity. R is equal to 50 and infinity. Compare 60 to 50. 50 is smaller, so we write 50 right here. 60 is smaller than infinity, so we write 60 right here. So now we have 70, 80, 50, 60. So you look and you say, well, that's not sorted. Well, we're not done. We did this, we did this. Now we need to combine this with this, except it's going to be the original value. So this will now be 70, 80, 50, and 60. So now we're ready to combine those. So when we get to here, we do the merge. So now what will happen is L will be equal to this. We said it was 70, 80, infinity. R will be equal to 50, 60, infinity. And then when we look back at A, we compare 50 to 70. 50 is smaller, so now we put 50 right there. Compare 70 to 60. 60 is smaller. We put 60 right there. So now we have 50, 60, 50, 60 in our array. We keep going. 70 is smaller than infinity. Put 70 there. And then 80 is smaller than infinity. Put 80 there. And at this point in time, array A is 50, 60, 70, 80. And then the other half is what it originally was, 40, 30, 20, 10. So what we would do next is we then come back up here, we go right, and we would go left again, come back up, go right, merge these two, come back up to here, go right, go left, come back up, go right, merge these two, then merge these two, then merge these two, and that's what happens. And so once again, if we look back at my program, we can see that's what happened. 70, 80 got merged together such that the order 50, 60 got merged together such that they're in order. Merge these two parts together, we get 50, 60, 70, 80. Then we go right. We fix the 30 and 40. So right here it was 40 and 30. We fix those to 30 and 40. Then we need to fix the 20 and the 10. We have 10 and 20. But see, these are not in the correct order, these four. We fix those 10, 20, 30, 40. And now we're ready to take this half and this half and merge them back together such that the entire thing is in order. And that is how merge sort works. In my next video, I will look at the algorithmic analysis to see what the order of growth is for this whole thing, to try to be able to compare this to other sorting algorithms.